Thanks for having me here. In my part of the session, I will move to talking about some real world challenges in building, testing of AI and machine learning systems. Uh, I represent a team with an emphasis, which is a platforms and product team. It's called the Infosys NIA. And in Swahili, we say NIA means purposeful. So it's a purposeful AI platform. And the platform was designed really for benefit of people and businesses to make enterprise consumption of AI and ML very easily. So the whole idea is while AI is an evolving area, but we also want the experience, the consumption experience for the businesses to be very, very easy. To have something which is an industrial grade AI and machine learning, and of course, have a variety of ways in which you can build, test, deploy, and host these. Now within this space itself, obviously when we began this, this was in 2014. We have collaborations today with Stanford, specifically the Stanford Dawn group, which focuses quite a bit on democratization of AI, and we also work with UIUC on this space. So if you look at the NIA platform itself, we have certain, as I said, foundational components. These foundational components include the natural language processing, ontologies, right? It's a lot of it is deep learning models. We have vision-based algorithms and so on. Today, specifically, all my use cases and challenges I will be speaking is in the space of documents, document processing per se, and how so that is going to be the area primarily because if you look at organizations, we realize that 70% of the enterprise data today is in unstructured form in form of documents, and being able to extract information from these documents is very, very critical step. So our entire focus is today, a lot of work we do with an emphasis is in the document AI space. Here, I just want to give you a quick preview. Infosys NIA itself is obviously, while we use a lot of open source, we have quite a bit of patterns in the space. We have found ourselves in several analysts and analyst related discussion. But I think what is most important today in today's context is speaking about three important use cases, which I will double click and specifically talk about the challenge. The first of those is really related to one of the America's largest telecommunication company, which was interested in processing a lot of their lease contracts. So these lease contracts are tower lease contracts they take all over the United States. And these are 20 years old lease contracts. And they wanted to digitize these lease contracts, read the information in the lease contracts to see where the opportunities they can have for the purpose of revenue leak detection per se, right? So essentially, that was one of the cases wherein we read about 8 million documents, 20 years old, poor quality, scanned copies, and we were trying to read these legal documents, and they were not in the same language per se, right? Each of these contracts would differ in the way the content is written, because it would come from multiple parties, multiple landlords trying to lease their towers to this company. So the language of these the contracts differed quite a bit. Uh, and this was, in that sense, I could say one of the largest machine learning projects because we had to process about 8 million contracts in a matter of a month. So we had to actually go ahead, extract certain clauses. And in this particular case, we had a huge business benefit because by reading these contracts, we could actually identify certain clauses. One of those clauses, for example, was related to rent reduction. So every time this tower lease is shared by another cell phone provider, uh, they would get 35% reduction in rent, which means if I can read these 8 million contracts and find out those contracts which have a rent reduction clause, and be able to get other statistics saying which are these towers which are shared by other cell phone providers, uh, then you can actually find out and claim or ask for these rent reduction. Specifically, there was another clause which is related to capital expenditure. So if you look at a lot of these companies have capital expenditure towards hosting towers and tower leases. If you look at a games arena stadium, right? Telecom communicator companies do contribute to the capital for the towers, and they are eligible for a refund. So unlike, let's say, an airport wherein a telecommunication company puts in a lot of capital infrastructure which cannot be refunded, these games arena is seasonal, right? So they do get. So by reading these contracts accurately, the company could actually save about 90 million USD, right? So that's the first use case. The second use case is one of the big five technology companies. I can give you an example. Today, let's say you're using a phone. Uh, each of these phone may have about 1,500 parts, which could be sourced from different suppliers across the world. So it is just not the performance or the specification of these phones have to be met, but people are talking about safety, right, which is beyond lead, right? So when you have, uh, you know, these components being manufactured by different suppliers, they have to send a chemical report. So they literally crush. Let's say you have your phone is crushed. The chemical composition is sent to various laboratories across the world, and each of these laboratories actually send you what components it has, the cadmium, different kinds of composition. And the company actually has to disclose to IPC 1753. So it's a way in which these companies disclose. So the key challenge we had was when you get so many varieties of documents across the world, all of the formats are different, different languages. How can you have a machine learning algorithm which can understand these formats and extract the information and be able to sort of harmonize it in a standard way like IPC 1753? So that was an important thing where obviously we were able to, with time, improve the productivity quite a bit, right? Reduce the cycle time, which was otherwise being done manually with a lot of errors. So that's the second thing. The third thing which happened very recently is related to COVID, and SBA came up with this Paycheck Protection Program, wherein a lot of small and medium-sized enterprises within US who were affected by the COVID outbreak could apply for loans. So when you submit these loan documents, you submit your lot of IRS forms. So being able to read these documents, right, find out what information resides in them is also important. So due to the surge of volumes, we had a bank coming to us, and we could process about 15,000 loans in a matter of 2 days. So these are the three use cases. My plan is to actually talk about quickly about how our systems are designed. So today within the Doc AI, we have a design which we say mimics the way the human brain works, right? In terms of we have an engine which has multiple neural pathways. So we take a document, we look at the document from the sense of text and text place classification, right? Reading the different sections, understanding what it means. For example, you may read a contract to see, okay, is because of COVID, is there a force majeure clause I can look at, right? So reading, understanding and classifying is one part. The second is, of course, you need to have the sequence and understand the context to it. So sequence to sequence kind of networks also we have, right? Third part is looking at it from the vision perspective, because a lot of information, vision-based algorithms provide orthogonal learning to what you learn from text, a completely different set of insights and inputs. So we have the vision-based algorithms. So we try to have an approach in most cases wherein we put them all together, and then we get much better and higher accuracy. So that's how the design of these systems are. Now, when we go for any real life applications of Doc AI, these are the three things which a customer really looks at. The first question is, what is the accuracy your systems can achieve? Second is how fast uh, both in terms of the response times of these systems, but also on the training time, right? How fast can you bring up the system and they can be up and running, right? That's the part. The third is it going to be cost effective, right? How much is it going to cost? So these are the three key expectations we see from the business side. Now, some of the practical challenges, again, I said my session is more or less going to be on the document and document related use cases. The first and foremost challenge which we face in any kind of the system is the data preparation. Before even you go into data extraction, if you look at the content which we get, lot of times it's handwritten content. You have watermarks, blurred images. So being able to orientation correction, so being able to clear up these stuff and get it in a format that the systems can do extraction, right? That's very important. The second part is that, though these may be a lot of it, may be machine learning, but there may be certain pieces. For example, we always find OCR creates a lot of confusion on visually ambiguous letters and numbers. And any of these contracts or documents, what we are most interested is the numbers, right? We could be reading some payment information, we may be reading dates, times, all of these are numbers. So unlike a spelling correction where you can have a contextual, language model built to correct the spellings, being able to apply machine learning, because this is not even a learnable problem per se, right? So if a number one becomes an I or a dollar becomes an eight because visually you cannot auto correct it. So what are the other ways of machine learning algorithms can be used, given that the straightforward spelling correction per se is not really relevant, right? Similarly, we also have other issues like, when you look at it, a lot of rich information. So if you have a 7.5%, let's say, increase in rent in a contract, that 7 1/2, which is a rich text with a certain property of a subscript, superscript, right? Or you may have some centimeter square of the material being tested, which is a mathematical representation, which is a rich text, but that gets converted to something very simplistic, like it could become a CM2, or the 7.5 could become 7112, because you've lost the font related properties and so on. So those are a lot of issues related to that. The third kind of information which we always find is different, most often critical information lies in tables. So being able to identify tables, different kinds of tables, right? Border tables, borderlets tables, tables which span across pages, uh, different kinds of orientation. So those are a very, very critical space. Alongside that, the language part. So we do have cases wherein it's just, even be it the voice recognition or be it these kinds of documents, it's never one language. Usually you have information present in multiple language, and that also uh, causes a lot of issues when you're dealing with the system, because even though you may be interested only in, let's say, extracting the English content, but still, if you do not understand what is there, these letters and characters of, let's say, in this case, a Japanese script could be converted or approximated to an English language, like, which will give you a lot of garbage. The last portion, of course, is, today in the document space, no document is in isolation. Usually you'll have a hierarchy of these documents, and you'll have to know how they are related to, and being able to classify these documents without even having to digitally do them. Because when we are looking at it and trying to do classification, let's say, of images, right, it's we do a vision based. So the key question is, can we do a vision-based classification for some of these documents and be able to create an hierarchy and link them, becomes very critical. Now, given these four challenges, I would actually, the good thing about my session is I'm just going to talk about problems and not the solution. One of the things, as I said, is, the telecom case, we had 8 million contracts, average of about 30 pages, and each document, because it's scanned copy, and we used to have images of towers, uh, land layouts there, we were about 3 MB, right? From these 8 million contracts, we landed up getting 2.4 billion paragraphs, right? And out of these 4 billion paragraphs, we roughly had about 30 intents. 30 intents per document means 30 paragraphs or 30 terms of importance. When I say 30 terms, one term could be a term related to contract preamble. Another intent could be related to rent, could be another preamble intent. The third one could be the termination clause, right, or the governing law. So these are the intents. So we had about 30 intent per document, and we also had to extract a lot of entities. So these entities are nothing but, you know, rent amount, percentage increase in rent, contract term, contract termination. So in all, we, if you look at these 88 million contracts, we had close to 24 million numeric entities to be extracted, which is rent amounts, percentage increase in rent, term, termination, and so on, right? Now, given the problems which I described above, uh, over 95% of the numerals were incorrectly recognized at the first time, right? So when we took these documents, processed them through an OCR tool, we realized every bit of it, right? About 65% of them had quality issues. And that's when we had to rely on certain ways. Here, of course, my session is not really going to talk about what did we do to handle the problem. But what I'm trying to say here is when you begin with a certain set of assumptions. But when you look at the data, we encounter problems and we try to keep iteratively adding newer pipelines, right? Which is what is a pipeline jungle per se, to be able to do this. So this is one kind of issue. The second issue which I want to talk about, right, is in the same situation, right, where we had 8 million contracts. We had, since this is not a case wherein you can go to the open source, be it ImageNet or other sources to get training data. These were all related to lease contracts. So we had to manually label them, and we had a team of lawyers who were actually labeling these data sets. We spent about 40K actually investing on these lawyers to train the machine, right? So we have a platform in which you can actually tag and create or label the data per se. And this was used to create ML. And finally, when the first iteration, when we built the ML model, we were shocked because after spending 2 months of effort and spending so much, we realized our accuracy was just about 54%. And what we realized was a very unexpected thing, that the most of the problems were because even though we had SMEs on board, right, 80% of the label data was incorrect. These were largely due to three reasons. The first reason was the lawyer's inability to know how to tag the data, inconsistency between the lawyers in the way they were tagging the data, and of course the third category was, the mistakes in them. But net this 18% of the label data was incorrect, which also brings us to a very important point about how do we ascertain whether the data which we take for labeling, right, is right. And this forms the foundation of being able to check the um, quality of the labels. The third use case, again, going back to the Big Five company, we had about 75,000 lab reports across the world, right? And these were obviously coming from different people, right? So the format, the language which is used, and not just the language, within English, the terms used to mean the same thing, right, were very different. Most of this information was in table and tabular data, and the tabular data also had a variety of variations. Right? So within the 75K report, we had 9,000 different variations. These variations meant different orientations of row columns. It meant different terms, right? The way they were using is all different, right? Again, there was a huge variance in the accuracy. So in certain cases, we were hitting a very low accuracy versus a certain cases where we were very, very high on the range. So then what we realized is that the documents, 20% of the documents which were in the low accuracy bucket had something in common, which was really about the multiple natural languages handling, right? The kind of mathematical symbols. So they use mu, sigma, beta, gamma, which were getting, sort of handling that was a problem. So this was the third challenge which I wanted to talk about. The fourth challenge again is, when we take these kinds of projects, right? In this particular case, I'm talking about the SBA PPA loan processing. We had about 15,000 loans, and each loan applicant would have 7 or 8 documents, which the person had to submit as a documentary evidence in order to be, eligible for this loan. Now, there was a huge variance, though a lot of these were, related to proofs about them filing tax returns, right? The number of employees they had, the wages of these employees, and so on. There was a lot of variations on how they had bundled it. Right? Many of them would actually join multiple years quarterly tax returns into one document, right? They had unnecessary documents which was not needed. They had provided a lot more than what was needed, and so on. So there was a huge variation, and what was needed is that in this kind of a case where you it's very, very risky to completely automate the system, because these machines are taking decisions about who would be granted a loan or not, right? So, what was very essential is that we had to really know what was the document and also have identify these discrete documents properly. So, if you have a bundle of documents, you need to break them up, even if the sequence is lost, into discrete documents. Classify the document level, not just based on the title, but even the page level you need to classify, and then you need to go ahead and extract, right, and make sure there are no duplicates and so on. So this is another thing wherein, we were having a lot of low accuracy in the first time when we did it, when we went with a title based classification and looking at only text and classifying. We were having a lot of miss, right? Which is when we had to go and change. So essentially what I'm trying to say is, when we try to meet these accuracy, I actually want to show you some of these samples so you can see what it looks like. This is the test report which I was talking about. If you look at it, right, two different languages, a lot of content is in tables. So if you do not handle the scripts of another language, even while you may be interested only in English, it could be a problem, right? And the same table within one report, right? If you see this page of the report versus this page, right, they're so different. The same thing is being presented. The other cases which I wanted to actually show is, if you look at this document, right, so you see it's tilted, right? There are a lot of black spots, scribbles written. So if you send this kind of document to an OCR tool, the tool will fail. So handling this was, very, very critical. See here, this is another document. So going back to what I was saying is that, while we did a lot of things, but we had to iteratively adopt many solution fallbacks. To begin with, we didn't guess, when we were in the test environment, we didn't think all kinds of combinations we would get in the production, right? So it had become, while we had beautiful self-contained packages, but we started writing a lot of code, uh, right? And our pipeline itself for data prep became very, very complex. So we started handling the pipeline to have cleanup, slant correction, DPI enhancements, binarization. We added that to handle the numerals, because you cannot correct the numbers. So we took an approach of inverse text normalization, wherein we would look at the text close to a numeral. For example, if it says $3,000 only as text, and then you had the number, we would take the $3,000 only and convert it as a numeral and then check. So approaches of this kind, wherever it's applicable, so inverse text normalization. Third is handling different language packs. and also mathematical extraction. So this to make sure all the rich text which we have, the information is not simply coded in, in certain and loses information, but we kept the font and the font related properties. Methods for visualization, this was very helpful, specifically in the case wherein we had our SME teams and we found that there were a lot of errors. It was very important for us to go into and do this TSNE visualizations, which would tell us about the interclass conflicts and which were those classes which were not, which needed better disambiguation. Fourth is, of course, applying effectively a lot of our algorithms, not just the text, right? The parallel pathway wherein you apply a text algorithm, but you also have other ways of doing it so that, in essence, you have a higher probability of predicting things rightly. So this essentially is the summarization, meaning there is no one perfect approach based on the production data. We land up iteratively changing and adopting a lot of solution feedback, which makes the QA very, very difficult, right? Be it in the case of the telecom where we had millions of records to review, it's a nightmare. So it's no more that clear boundary like traditional systems where you clearly test, you have a QA, and then you roll it out in the production. This becomes a continuous stream. So that is what I want to summarize with by saying that, today it's become very, very complex. I do not think we have a great answer to this really in the practice side of things. Of course, one of the papers which really inspires is this paper written by a Google team on this hidden technical debt in machine learning. A lot of the concept they present seems to resonate very well in the practice, but again, what we have is a whole bunch of problems, and I would say in this journey of finding the ways to handle, we are possibly very, very early on. With this, I conclude my session.